Dear colleagues and audience at the 学术之 Stanford, welcome to attend today's Professor Michael Rathjen's lecture tonight. It's a welcome first to introduce tonight's speaker, Professor Michael Rathjen. Academic position, he currently is a full professor at the School of Mathematics at the University of Leeds in UK, and has held positions in a number of universities, among which Ohio State University, Stanford University, UCLA, University of Master Education. He got his diploma in mathematics and university master, and also he obtained a PhD at the University of Master. He works on many fields, including proof theory, intuitionism, and constructive mathematics, reverse mathematics, and combinatorial principles, constructive set theory, Martin-Loop type theory. Contributions. His most outstanding achievements belongs to ordinal analysis, the most complicated and technically advanced area of the field, with the exciting interplay with recursion theory, set theory, and model theory. He has also made significant contributions to explicit mathematics, constructive set theory, and Martin-Loop type theory. Honors, here I just leave some. He was the invited speaker at the International Conference of Mathematicians, Madrid. He was tutorial lectures, plenary speakers, and logical colloquium at different years. Also, he was plenary speakers at the SL, North American Annual Meetings. He was also speakers of the well-known Lindstrom Lecture, Scollins Lecture, Henting Lecture, Goodstein Lecture. He has published more than 100 articles in journals and collections. He is the editor of Bulletin of Symbolic Logic. He was editor, Journal of Symbolic Logic, also editorial board in Perspective of Mathematical Logic. He was the editor of Oxford Logical Guides, 2016 to present. Okay, during the lecture, if you have questions, you're welcome to post your question at the 学术之 Stanford. We will not record the question section, so don't worry about your appearance and be free to ask questions if you have. Okay, now it's time for Professor Michael Rathjen's lecture. Please and welcome. He will talk about the art of ordinal analysis. Okay, please.
Okay, yeah, good evening in China and good day everywhere else. First of all, I'd like to thank Professor Yang Chang for this invitation. So it's very prestigious to give such a presentation on China. Let me bring up the slides. So the title of the slides is Ordinal Analysis, or rather the Art of Ordinal Analysis. So ordinal analysis is a technically quite demanding area of proof theory. And my idea with these lectures is that I would like to give you the flavor and of this area and not go too much into technical details. But on the other hand, I think one cannot appreciate the area if one hasn't seen any technical details. So most of the technical details I will just flesh up and continue. Okay. And if you have any short questions during the talk, okay, that's also fine by me. I'm happy to take them. Okay. So the plan of the talk is I would like to start in the first part with the history of ordinal analysis. And in the second part, I would like to show you some ordinal representation systems and how an ordinal analysis of a set theory can be approached, and what are the obstacles. And the third part is about applications. So with ordinal analysis, many results have been proved, and very often there are no other proofs available. Okay. As you know, proof theory, Beweis theory in German, is something that started with Hilbert. He gave his famous address in Paris in 1900, and among the problems, the famous Hilbert problems, the first two of them are actually problems in the foundations of mathematics, in mathematical logic. And the first problem is probably the most famous. It's about the axiom of choice and the continuum hypothesis. The second problem is the problem of the consistency of analysis. So analysis, well, let's say this is the theory of the real numbers, continuous functions, differential functions. So what you really need to do mathematics. And Hilbert wanted to provide a proof of the consistency of analysis. At that time, in 1900, he didn't have a clear idea how this could be achieved. This later became, much later actually, 20 years later, more than 20 years later, became Hilbert's program, where he devised a plan how to prove the consistency of large chunks of mathematics. Of course, the background for asking for consistency proofs were developments in the late 19th century. So paradoxes were found by Cantor, for instance, in 1895, communicated to Hilbert in 1896. Then the same was rediscovered by Burali-Forti. Zermelo also discovered a paradox in set theory in 1900, and this was rediscovered by Russell in 1901, Russell's paradox. And there were very famous mathematicians who were deeply concerned about the paradoxes and whether mathematics could be infested by paradoxes. Proof theory proper. Well, let me say a little bit about the history. So in Dedekind in the late 19th century, basically coined the notion of an arbitrary structure and structural definition. But he added an important condition, namely that one has to prove the existence of a system, so an abstract structure of things falling under the notion to ensure it does not contain internal contradictions. So here we have the notion of a contradiction being, the avoidance of contradiction being central to when you invent new notions in mathematics. Hilbert in 1904 gave in a nutshell, in a very rudimentary form, sketched a consistency proof for a weak system of arithmetic. What is interesting about this is that he didn't use any evidence or any models for that, but he looked at a syntactic consistency proof. And so he looked at really how proofs are generated in a formal system. In his famous talk from 1917, Axiomatic Thinking, he said we must turn the concept of a specifically mathematical proof itself into an object of investigation. This is interesting. Maybe not. One should realize that the notion of proof never became really an object of mathematics itself until the 20th century. But then from 1970, it took a while for Hilbert to come up with his consistency program. It was mainly conceived in the winter of 1921-22. In the meantime, he again flirted with logicism. So Hilbert's program, just very briefly, the idea was to codify the whole of mathematical reasoning in a form of theory T and then prove its consistency by means that are unquestionable. Unquestionable in the following sense that, well, there's a certain amount of background you need to assume for any scientific investigation. And this basic part of reasoning, Hilbert called finitistic means. And to carry out this task, to provide this consistency proof, Hilbert inaugurated a new mathematical discipline, and that's device theory or proof theory. So here, proofs themselves become mathematical objects. Now, this consistency program that Hilbert proposed was pursued by some of his students. Ackermann, in his dissertation in 1925, he gave a consistency proof for what one could call a second-order version of primitive recursive arithmetic. So here, second-order version means that the system also has free variables for functions from naturals to naturals. And the interesting thing about Ackermann's proof is that he used mostly finitistic means, but then he also used something else. He used the transfinite induction, not for arbitrary properties, but just for decidable properties. And this transfinite induction went up to the ordinal omega and then raised to the power omega to the omega. And so here we have for the first time an association of an ordinal with a formal theory. Okay, now one thing that plays a big role in ordinal theoretic proof theory is ordinals, but not set theoretic naked ordinals, as it were, but ordinals which can be represented in an elementary way. And for a long time, actually, proof theorists could draw on Cantor. So Cantor proved this normal form for ordinals, namely, if you have an ordinal non-zero, then it can be represented in a unique way as follows. It can be written as a sum of omega powers, where the exponents, beta 0 and so on, to beta n, they are weakly descending. So the Cantor normal form. And this Cantor normal form was then famously used by Jensen to provide a proof, a consistency proof for first-order arithmetic, for piano arithmetic. Okay, and so on representation, in this case here, in Cantor's normal form, it can actually happen that if n happens to be 0, it could actually happen that beta 0 is the same as beta. So then, but the idea would be that to have a representation for an ordinal beta, it should be in terms of smaller ordinals. Yeah? And this can be done up to a certain ordinal, namely up to the ordinal epsilon 0, which is the first ordinal bigger than 0 that has this property that if an ordinal beta is smaller than it, then also omega to the beta is smaller. And then you can see that if you take Cantor normal forms below epsilon 0, then you can code them in the natural numbers. And so you get a reflection of the ordinals up to epsilon 0 on the natural numbers. And it turns out it's actually, this representation system has a very low complexity. Computationally, it's of complexity way below primitive recursive. You can formalize such representation systems, and that actually applies to all representation systems that have been used in proof theory. You can represent them in bounded arithmetic, so very weak fragment of even primitive recursive arithmetic. In particular, so bounded arithmetic means that all these representations have a very low complexity. Now, Gensen then showed that if you allow transfinite induction up to this ordinal epsilon 0, then you can prove the consistency of PI arithmetic, first order arithmetic. And what is also important to note about this is that the application of transfinite induction is not applied to arbitrary formulas. It's actually applied only to primitive recursive, or actually very, very computationally very low predicates, besides using finitistically justified means. And so Gensen's result then leads to a nice rendering of Hilbert's program. Namely, what he did, you can summarize as follows. You can say that what Gensen did is using F as a name for a theory that is acceptable finitistically. Okay, so this F is supposed to be a formal theory that encapsulates finitism and finitistic principles. And then in addition, one needs a certain amount of transfinite induction to prove the consistency of PA. So this just means the con PA means the consistency of PA. And PR, TR epsilon 0, this is supposed to be an abbreviation for transfinite induction up to epsilon 0, but only for primitive recursive predicates. You could even restrict the predicates for which you use it, but it's not so important today. Okay, and then moreover, Gensen also showed that you cannot use a smaller ordinal. You cannot do it with an ordinal alpha which is less than epsilon 0. So this gives you a nice picture, and the compelling picture is that there is a non-finitist part of PA which is encapsulated in this transfinite induction up to epsilon 0 for these primitive recursive predicates. And well, and then not only PA, but you might want to do it for other theories. And so the idea is to assign an ordinal which measures the strengths of the theory, the proof theoretic ordinal. And okay, a very sloppy way of writing it could be the proof theoretic ordinal of T is the least alpha, such that primitive recursive arithmetic, well, that's basically our theory that encapsulates finitistic reasoning, plus primitive recursive induction up to alpha yields the consistency of T. Okay. So here, the least alpha is a bit, this is the sloppy part of it, because it only makes sense if we refer to a ordinal representation system which is given to us beforehand. Okay. Right, so Gensen is the really the founder of ordinal theoretic proof theory, and the development of proof theory after Gensen, one can sometimes separate two strands. One is, so you have to do something to prove, yeah? And the main technique that was invented by Ganson is the cut elimination technique. But also one needs for stronger, much stronger theories than PAA, and actually for theories stronger than ones that are called predicative. You need also another technique which is called proof collapsing, where you have infinite proofs, and these infinite proofs can somehow be collapsed into proofs where you remove certain strong impredicative principles. Okay, and the other strand one can distinguish is ordinal representation system. As I said, so to make sense of this definition of proof theoretic ordinal, one needs to have a supply of ordinal representation systems. And some people in the 60s just kept on developing ever stronger ordinal representation systems without using that stuff for any proof theoretic analysis. Okay, so just very brief, I'm assuming that you know the sequent calculus. So this is one of the inventions, great inventions of Ganson. He also invented natural deduction. The idea of the sequent calculus is, okay, so basically you look at sequence. This is an expression of this form, gamma arrow delta, where gamma and delta are just finite sets or finite sequences of formulas, say A1 up to AN, BA1 to BN respectively, and then the idea is to read this gamma arrow, so this big arrow, gamma arrow delta is to be read informally as gamma yields delta, where you view the stuff in gamma, so the AIs, as being the conjunction of the AIs, and delta containing the formulas BI, well, here we view the BI to BM as a disjunction. Yeah. Okay. And then the beautiful calculus that Ganson invented, basically you have two rules for every logical particle. So here for negation and implication. So for the implication, I just use this simple arrow here. And then this pattern continues for the particles that we have for propositional logic, but then also for quantifiers. And so that's how you encapsulate logical reasoning and the sequent calculus. And you have to start somewhere, so you also have identity axioms. Well, I call them identity axioms here, A arrow A. And then the sequent calculus also has a rule, a cut. Yeah? And the cut rule is distinguished from all the other rules in that if you look at the conclusion of the cut rule, so here you have gamma arrow delta A and A lambda arrow theta, say, and then this A disappears, it's cut away. And so this is a generalization of the usual cut in this particular example here. B arrow A arrow C, and then you conclude B arrow C, and the A is gone. And this is not the case for all the other rules, because basically the formulas you use to infer a new formula. So for instance, in the case of quantifiers, you see that in some sense, the F is preserved in the conclusion. So nothing completely disappears, although the term T is not present in the conclusion here. Okay. And so Ganson, and then also other rules which are of no interest right now. I'd just like to mention one thing, which is also beautiful about Ganson's sequent calculus, namely that in it you can express classical logic and intuitionistic logic simultaneously. And it's just a small change. Well, it appears to be a small change, but intuitionistic reasoning is obtained by just imposing one constraint, namely you only look at sequence gamma arrow delta, where this delta is not too big, namely delta consists of at most one formula. It might also be empty. Yeah. And okay, so that's Jensen's beautiful sequent calculus. I will not go through examples because I'm assuming you know them. But here's a classical example. It's extruded middle, and you see this imposition that there's only one formula allowed to, at most one formula allowed to occur on the right-hand side of the arrow is violated here. And so here we have several formulas on the right-hand side in line 2, 3, 4, 5. And you deduce something which you know is intuitionistically not allowed, A or not A, for arbitrary formulas A. Okay, and intuitionistic examples, here's an intuitionistic example, and here you see just you want to deduce not there exists x, fx implies for all x, not fx, and that's intuitionistically valid. And you just have to see that the deduction obeys this restriction that there's at most one formula on the right-hand side, and you see there, it's fine. Okay, so then the main thing that Jensen proved in 1934 is that we have cut elimination, that actually these cuts can be avoided. So if you have a proof with cuts, then of a sequent gamma arrow delta, then you can also get it without cuts. And okay. And this cut elimination theorem is quite powerful. You get lots of interesting corollaries. One is the subformula property, namely, if you have a proof of a sequent gamma arrow delta, then in the proof, you only need to use, so then there is also a proof. If it's provable, okay. There are lots of different proofs with lots of cuts, perhaps. But then, when you turn it into a cut-free proof, then the deduction contains solely formulas that are subformulas of formulas in gamma and delta. And in particular, you see immediately that no contradiction can be arrived at in this way. The contradiction being, signified by the empty sequent. Okay. And then lots of interesting results from traditional proof theory follow from Jensen's Hauptsatz, Elbrand's theorem, and so on, Hilbert-Ackermann consistency, and also you can deduce easily that if T is a geometric theory, then, and you have a classical proof of a geometric implication, then there's also an intuitionistic proof of it. I haven't explained what this is, but I just wanted to convey here that the Hauptsatz is extremely powerful when it comes to proving or showing that these traditional results due to Elbrand and Ackermann and sometimes what's called the geometric theories, classical geometric theories are conservative over intuitionistic. The intuitionistic counterpart for geometric implication that's sometimes called Barr's theorem. All of this follows from Jensen's Hauptsatz. Okay, but usually, so this was just about pure logic, but usually we do not want to just look at pure logic. We are interested in theories, and theories have additional axioms. And then cut elimination is not always possible. Although cut elimination is possible to a certain degree, namely, you can avoid cuts that with formulae that have a complexity higher than the axioms of theory. Okay, and that leads to partial cut elimination. It's also very useful tool. Okay, now a little bit about Jensen's proof. So how did Jensen prove the consistency of PA? And actually, he didn't do it he didn't do it by cutting it, he did it in a certain other way. So this famous proof from 1938, what Jensen did is, so he wanted to prove the consistency of PA, okay? And so the first thing he did, he assigned to deductions in PA, he assigned ordinals. That's already a very cunning way of viewing proofs. And it's not just the it's not the length of the proofs, of course, because here we are dealing with proofs in PA, so they are finite anyway. So it's something else. It's something about the structure of these proofs that you have to have a deep insight into. And okay, that's what he did. And then he also found a reduction procedure R, which turns a proof D of the empty sequent, so that encapsulates inconsistency, into another proof of the empty sequent, R of D, in such a way that the ordinal assigned to R of D is smaller than the ordinal of D. Then you see here, this cannot go on forever if these ordinals are well-founded, yes? And also this reduction operator is a primitive recursive operator. So it takes a deduction D of an empty sequent into another deduction RD. This is an effective procedure. Okay, and that's what Jensen did. And just one aside here. So Paul Cohen is, of course, famous for his proof of the independence of CH and AC from ZF. But what's probably not so well known is when Paul Cohen started his career in logic, as it were, the first problem he tried to solve is Hilbert's second problem, so the consistency of analysis. And he ran into trouble and then turned to the first problem on Hilbert's list. But in a certain sense, Paul Cohen never gave up on this. So when I was at Stanford in the 1990s, the middle 1990s, so Cohen thought that he had a proof of the consistency of second-order arithmetic, and it was somehow, in a certain sense, he drew on Gensen's work. So he did his own proofs of Gensen's consistency proof. So he was fascinated by that. Okay, so this didn't work out. So he turned out that the proof was wrong and couldn't be salvaged. But there's an interesting idea that Cohen, I think, was pursuing. And so the idea is that in some sense, when you want to prove the consistency of a theory, you look at deductions in the theory, especially deductions of existential statements, which assert the existence of certain objects. And so if you want to prove the consistency of a theory, you somehow have to accept the existence of these objects that are proved to exist in the theory. And then as you go on, you prove the existence of more and more objects that you have to accept. And in a certain sense, ordinal analysis can be viewed in that way. At least I view it somehow in this way, namely that you start out giving names to objects that are provable in a theory, and in this way you arrive at some kind of miniature universe. And so if you do proof theory of set theory in particular, then you see that you arrive at some kind of miniature version of a universe which shows you the consistency of that set theory you're analyzing. Anyway, so here's just a quote, and this quote is from a paper which I think appeared in 1971, Comments on the Foundations of Set Theory. So he says, since I feel it incumbent on me, having chosen formalism, so he said he's a formalist, to explain why I do not advocate abolishing all infinitistic mathematics, I should like to put forward the view that we do set theory because we feel we have an informal consistency proof for it. So I also view, like Gensen and like Cohen, I also view these ordinal analysis actually as real inconsistency proofs, where you create somehow a miniature universe and then you convince yourself that this is consistent. Okay. Just one thing, even if you're not interested in consistency per se, you get interesting results from these ordinal analyses. So independent proofs became very, very fashionable in mathematical logic in the 1970s. But actually, you could have obtained several independent proofs much earlier. And for instance, from Gensen's work, it follows that we have a nice independence result, which is not of the consistency flavor, namely that you have this independence result that if you look at epsilon zero as a representation system, then you can show that in PA you cannot prove that primitive recursive sequences of ordinals below epsilon zero that they cannot be infinite. So this PRWO epsilon zero says there are no infinitely descending primitive recursive sequences of ordinals below epsilon zero. So that's a pi 02 statement, and it directly follows from Gensen's work that this pi 02 statement is not provable in PA. So it's a mathematical statement. It talks about basically a fragment of talks about Cantor's ordinal representation system for epsilon zero. And then people who actually at the time realized that this is correct. Among them you find Goodstein. So in 1944 he proved that Goodstein sequences. So what you do is you look at natural numbers and then write them in a certain number form, and you make certain changes, and that if you do these changes, that this eventually terminates. So these are the Goodstein sequences. And he showed that, termination of primitive recursive Goodstein sequences is not provable in PA, but he didn't express it in that way. Okay, so now there's one strange thing about proof theory, which happened after Hilbert, namely that, and after Gensen. So the idea was that you want to have some kind of finitistic proof for the consistency, because it was really the infinite that was a concern to Hilbert. But then after Gensen, proof theory actually turned infinite. And in particular, one person who was instrumental in developing infinite proof theory is Kurt Schütte. It might seem counterintuitive that proof theories turn to infinite proofs, but it turns out that the treatment of infinite proofs can be also done in a finitistic way. I'm not going to talk about that. There are quite a number of papers in the literature, and particularly also you can look at the Handbook of Mathematical Logic. There's a paper by Helmut Schlichtenberg where he shows how infinite proofs can be treated in a finitistic way. Okay. So going infinite means we add an infinite rule in the case of piano arithmetic. And so you have infinitely many premises here if you want to deduce, say, a universal statement about numbers. Yeah? So you have these infinitely many premises. And it turns out that if you do this move, actually, then this infinite version of PA allows catenation. Basically, you have the Hauptsatz for this infinite system, and it works very well. You can use Gensen's techniques also for infinitary logics. And okay, so this infinite version, let's call it PA omega, and then it turns out there is the really strong principle that you have in PA is the induction schema. But it turns out that in the infinite version, well, you don't need to add the induction schema axiomatically. You can just outright prove it in the infinite version with the omega rule. Okay, and then you have similar things. You have so you have the Hauptsatz there, and here we just use this notation here. So D is supposed to stand for an infinite deduction of a sequent gamma arrow delta, and then you want to measure somehow the complexity of these infinite derivations. And the upper ordinal basically tells you something about the depth of this tree as a well-founded tree. And K is supposed to be is a natural number that takes into account what kind of cuts you do. And K here means that only cuts with formulas of cut rank less than K are allowed in the deduction. But then basically it's you can then get Jensen's Hauptsatz, as I said before. So first of all, the formula system PA itself can be easily embedded into the infinitary system. Here you incur deductions of length omega plus m is a natural number here. And then you do cut elimination, and of course you have a cost here. So if you have two deductions, and you want to cut a formula A here, and this A has the complexity, has a cut rank K, where you could do the cut, but then the resulting derivation would have cut rank K plus 1. If you want to avoid this, what you do is, you can do this, you can avoid this, but then the deduction itself becomes longer. And the length is basically alpha plus beta. And here we use the Hessenberg or natural sum, which means that, in the infinite case, if you do alpha plus beta, parts of alpha can disappear. And the natural sum avoids this. There's no disappearance of parts of these ordinals. Okay, and then we get cut elimination. And you see here, naturally, if you start with an ordinal alpha less than epsilon 0, and this is still less than epsilon 0, this omega tower with alpha on top. But as you see here that you approach epsilon 0. Okay, so that was just repeating Jensen's work. And now, the real goal of ordinal analysis was not PA, but was second-order arithmetic, in which one felt basically one could develop most of mathematics. And in second-order arithmetic, so here we have also quantifiers over sets of numbers. So these uppercase letters X. And in this calculus, GLC, for second-order arithmetic, you see the comprehension. So here one has comprehension for arbitrary formulas, and the comprehension is basically baked into the formal rules. And let's look at the rule for an existential quantifier introduced on the right-hand side. So here we can use basically these kind of comprehension terms. So one has comprehension terms here. And so this comprehension term, the set of all numbers V such that AV, it stands for a set, and you see that if you can deduce F of this comprehension term, then there exists a set of natural numbers X, so the F of X. And so this really encapsulates second-order comprehension. And now the goal was really, Tercuti basically took up or continued Jensen's program, and he wanted to continue it to the second-order arithmetic. And his conjecture, which he formulated in the late 1940s, was that also the second-order arithmetic, or this Jensen style version of it, allows cut elimination. So the fundamental conjecture is that this system allows cut elimination, and actually not only for second-order arithmetic, but also for nth-order arithmetic. And this became known as Tercuti's Hauptsatz, or actually, it was his fundamental conjecture. And it's not Tercuti's Hauptsatz. It wasn't proved by Tercuti, and it wasn't proved in the way Tercuti wanted it. Okay, first of all, let me just quote this, what he said in the 1940s. He, having proposed the fundamental conjecture, I concentrated on its proof and spent several years in an anguished struggle trying to resolve the problem day and night. Okay, so this is what you can tell your PhD students. It was proved, so the fundamental conjecture was proved, but it was proved by set theoretic means, basically, and Tachuti said that this is not what he wanted. Okay. So, but Tachuti then became, yeah, he said, well, actually, so maybe it's too much to do basically to prove the Hauptsatz in a constructive way, or prove consistency of second-order arithmetic. Instead, he concentrated on fragments of second-order arithmetic, and the fragment he then concentrated on was the one based on pi11 comprehension. So the quote here says that with all that, the subsystems for which I have been able to prove the fundamental conjecture are the systems with pi11 comprehension and a slightly stronger system, delta 1-1, delta 1-2 comprehension. Okay. And then he said this was my last successful result in this area. And then these things were basically proved in the late 1960s. Okay. So just a reminder of second-order arithmetic, it's a formal system which extends PA. So in addition to variables over numbers, we have variables over sets of numbers. And the strong axiom schema that you add is the comprehension schema here. So that whenever you have a property expressible in the language of second-order arithmetic, then also the collection of all naturals satisfying P is a set. Okay. And then I will just refer to pi11 comprehension. So it's the usual classification where you look at formulas where you start with a bunch of alternating second-order quantifiers followed by a matrix which only contains quantifiers over numbers. And if you start with a universal quantifier over sets followed by an arithmetical matrix, that's pi11. And then basically one classification of the strengths of subsystems of Z2 is by asking how much comprehension do they allow. Okay. And let me just intersperse some remarks about what kind of axioms actually and systems do you need to do mathematics. It was realized by many people, also by Hilbert and Bernays, that it's only a fragment, a small fragment of ZFC that one uses in most of mathematics. This was also said by not by Jensen, but by Gödel. He said in 1951 that it is safe to say that 99.9% of present-day mathematics is contained in the first three levels of this hierarchy. So here he was referring to basically the von Neumann hierarchy above the omega. Minimalism looks at what one really needs to do most or much of mathematics. This already started with Hermann Weyl, who was really the founder of this kind of enterprise in his Das Continuum from 1918, where he was very concerned and disturbed by the foundational crisis. And the foundational crisis issue is an expression that was coined by him. And in 1918, he made an attempt to say, okay, let's throw away all these dubitable principles and just work with things that we can believe in. And he tried to resurrect much of traditional analysis in this way. And then, as you know, logicians then turned to this question, for instance, in the 1970s, and among them also Takuti and Sol Pfefferman. And the result was that actually they tried to develop much of mathematics within systems that do not have a greater proof-theoretic strength than PA, than first-order number theory. And it's quite amazing that this works. Yeah? And then a more refined program was also started by Harvey Friedman and Steve Simpson, called reverse mathematics. Okay. Sometimes there are different views, of course. This program, of course, of reverse mathematics is something that is dear to also to Harvey Friedman. But when it comes to new axioms, he has in recent years developed a machinery, or let's say, which was called Boolean relation theory originally, but now has a different name, where he wanted to show that actually the large cardinal axioms of set theory can have an impact on ordinary mathematics, or let's say it in another way, might have or should have an impact on ordinary mathematics of the future. And here's a picture, and it's not a picture that I particularly like, but I just took it from a journal article. And so this guy is kind of hitting a wall with mathematical science, as science with an X, and it's from this journal article. And so the journal article appeared in the Nautilus magazine in February 2017. And so it has these pictures here in the article. The first is, of course, Harvey Friedman. And it says, this man is about to blow up mathematics. And furthermore, Harvey Friedman is about to bring incompleteness and infinity out of quarantine, I mean. And you see here this strange next photograph, and I think it's supposed to be a photograph of a huge cardinal, or a large cardinal. Anyway, so that's the story of how much of second arithmetic is needed. As I said, started with Hermann Weyl in 1918. And Hilbert Bernays and many other people then contributed to it. Okay, and in particular in this program of reverse mathematics, they singled out a bunch of subsystems of Z2, which are used to basically, which are landmarks for classifying principles of ordinary mathematics, and in particular they singled out 5 subsystems of Z2. The first one, recursive comprehension, is of the same strength as primitive recursive arithmetic, and so is the next one, WKL0, but one has a stronger axiom here, Koenig's lemma. The third one, based on arithmetic comprehension, is of the same strength as piano arithmetic. And then there are 2 further ones. ATR0 is a subsystem where you can do arithmetic transfinite recursion. And then pi11 comprehension, that's the ballpark where Takuti received his ordinal analyses or consistency proofs. Okay. And I will come to this, back to this later, but let me just briefly mention some results. So in RCA0, you can prove things like algebraic closure of fields. In WKL0, you get Cauchy-Piano. You can solve differential equations. Hahn-Banach also holds there, and so on. In ACA0, you have the Bolzano-Weierstrass theorem. And in pi11, you can show something about the abelian, countable abelian groups. Ohm's theorem. Okay, now predicative proof theory. I will not show you the details of these calculi, but there is a way of, if you want to go into proofs, it's sometimes easier to deal not with the full-fledged Ganson calculus, But to look basically at a, I would call it a classical fragment of it. And a classical fragment has the nice property of humans that you have very, very few rules. Yeah. And basically, what you do is you look at formulas in negation normal form, where you push the negations inside in front of the atoms. Okay. And then you actually can deal with a so-called one-sided calculus. So Gansen had this two-sided calculus, but basically you can do it a one-sided calculus. So if you have A1 up to AR is the antecedent part of your sequence, then you can identify it classically with a one-sided version of it, where you just write the negation of these, and you just put the negation of these onto the right-hand side. Yeah. And then you have a very simple so-called Tate calculus, where the rules are fewer and easier to, usually I do not like this calculus, but it's good if you really want to go into, if you want to do it quickly. And okay, that's so important. I just want to mention some things that happened then in the 1960s, namely that so analyzing various subsystems of second-order arithmetic, in particular, Kurt Schütte used infinitary calculi, which are somehow modeled on the constructible hierarchy. Well, to be more precise, on the constructible hierarchy as basically its reflection just on sets of natural numbers. Yeah. But you basically keep the constructible hierarchy, but then you look at only at sets of natural numbers, and as they are generated at various levels of this hierarchy. And so Schütte was a master of this area. He proved lots of very interesting theorems in this area. That happens in the 1960s. Okay, and you see here, so I wrote in a very sloppy way that the proof-theoretic ordinal of a system R, A sub alpha is phi alpha 0. That refers to an ordinal analysis. Okay, so I just skipped these infinitary systems. So for these new systems, one has to go beyond epsilon 0. And proof theorists actually could, again, rely on work of other people. So Gansen relied on work of Cantor's. For the analysis that Schütte did, for instance, in the 1960s, he could rely on Veblen's work. And Veblen was inspired by Hardy. And Hardy did some kind of a certain ordinal representation system. His goal was to construct a subset of the reals of size out of 1. And so Veblen invented a hierarchy of functions where you start with some function f. Now let's say, you start with a function f, and then you take derivatives of these functions. What does derivative mean? So let's say the starting function is just the omega to the xi function. Then at successor stages, at successor ordinals, what you do is you take the derivative of the previous function, phi alpha. And what does the derivative mean? The derivative is the function that enumerates all the fixed points of the previous function. And that you can do in set theory. And at limit stages, you just take the function that enumerates all the fixed points of the previous function, in the sense that are all the ordinals that are fixed points of all previous functions simultaneously. And that then gives you another normal form, the so-called Veblen normal form. And okay, and here it's similar to the Cantor normal form. So every ordinal bigger than 0 can be written in this particular way here, with these 5 functions. And so here you have that, you have that these ordinals here in the sum are weakly descending. and you also require that the input eta I, that they are smaller than phi psi I eta I. Okay, then there's an ordinal which you can, then you can get an ordinal representation system, and in this case, the role of epsilon zero is played by an ordinal gamma zero. So the first ordinal cannot be expressed in this representation system. And how does it work? It's the least ordinal bigger than zero, so that every other ordinal, every smaller ordinal, you take smaller ordinals alpha and beta, then phi alpha of beta is still smaller than this gamma here. And it's kind of a famous ordinal because it's identified with, or it's the limit of some kind of autonomous progressions of theories, which gives rise to a certain notion of predicatility. Okay, and then you see you can prove in this, then you can prove certain catenation theorems for ramified analysis. And so the first catenation theorem is the same as what Gensen did. You want to lower the cut rank from eta plus 1 to eta, or rather say the infinite version of that by Schütte. And then you have also, then you need a more elaborate catenation theorem, because you also can have, you also can have now cut ranks that are transfinite. And here you need a second catenation theorem, and that you achieve by using the phi function. Okay. And just a very brief picture of ordinal analyses related to those distinguished systems of reverse mathematics. So if you do ordinal analysis, you can, so RCA0 and WKA0, the first two systems, just have ordinal omega to the omega. Yeah. And then, as I said, ACA0 is basically the second order version of the arithmetic. That's epsilon zero. The phi function comes into play when you, for instance, so this ACA0 has only an induction axiom for sets of natural numbers. But if you add the induction scheme, you get a stronger system, and that the strength of that system can be measured using the phi function. So it's phi 1 of epsilon 0, or in other words, it's epsilon of epsilon 0. Okay. And then starting with the top one of the previous slide here at the bottom, then you can go up in this hierarchy and you see the phi function can be used to express the strengths of kind of signature systems like based on delta 1-1 comprehension or based on sigma 1-1 dependent choice and so on. And then gamma 0 shows up as the proof-threaded ordinal of ATR0. So it's the, how many systems do we have? It's the fourth system, the fourth of the systems usually used by reverse mathematics. Rathjen did much more than just, investigating normal forms with his binary phi function. He also did n-ary phi functions, and actually he also did phi functions which can take transfinitely many arguments, where only finitely many of the inputs are allowed to be non-zero at a given time. And that gives you the big Rathjen number. But this is still not enough if you want to analyze significant set theories or fragments of set theories. And there was a big step taken by Bachmann in the 1950s. And it's a similar move as the move from finite derivations to infinite derivations. So what happens here is Bachmann actually to come up with an ordinal representation system, which is a countable object. Yeah? He actually had the idea of using uncountable objects, namely uncountable cardinals. And he used them in a very cunning way to develop stronger ordinal representation systems. And I do not want you to read this slide. It's just these uncountable ordinals play a role in the diagonalization process. Okay. And so the first system I'd like to look at is Kripke-Platek set theory and an ordinal analysis of that. I just will sketch it very, very briefly. And so the crucial axioms of Kripke-Platek are, so first of all, you have the separation axioms are restricted to so-called delta zero formulas. Delta zero formulas are formulas where the quantifiers over sets can only appear in a bounded form. And bounded means they're of the form for all x in a given set A, or there is a y in a given set B. Only such formulas can be used in the separation scheme and also in the collection scheme. And the other strong axiom of Kripke-Platek is you have the general induction scheme for elementary induction. Okay, so here are just just a summary of the axioms. You have the usual axioms like extensionality, paired union, infinity. You have infinity axiom. But then separation, as I said, is restricted to formulas F that are delta zero, have only bounded quantifiers. And the collection axiom also has this requirement that if you have a situation for all x in A, there's a y, gx, y, then you can collect enough of these y's into a set Z, yeah? But this only is allowed for delta zero formulas G. Okay. And in the ordinal analysis of Kripke-Platek, one uses a formal counterpart of the constructible hierarchy, where the levels L alpha here, where the alphas come from an ordinal representation system. And I will just go through this very, very briefly. So what the formal infinitary system one generates has these kind of terms, basic terms, L alpha, for chunks of the constructible hierarchy, where the alpha is less than a big omega. I will say more about the big omega shortly. And then if you have formal expressions of this form here, x and L alpha, fx, and then some other parameters, and again, this L alpha here as a superscript means you restrict all the quantifiers to L alpha. Then this is a term in the infinitary system. And you use these terms to basically deduce delta zero separation. Okay. And then you have an infinitary system. An interesting thing is that these terms allow you to introduce infinitary rules, okay? And you see, for instance, in the rule for the bounded universal quantifier here, if you want to deduce gamma comma for all x in T fx, you allow, you have to prove first for all terms S that are of a lower ordinal than the term T, you have to prove gamma comma S and T than F of S. So that's usually it's an infinitary rule here. Yeah. And you see it even more pronounced here in the for all rule. Here you have to first prove gamma comma Fs for all terms of the infinitary system to conclude gamma comma for all x Fs. Okay. And then in addition you have cuts, and you have also a strong rule, the reflection rule here. Reflection rule for sigma formulas. So sigma formulas are formulas where you allow unbounded existential quantifiers, but otherwise you only allow bounded quantifiers. And this rule here, this rule here, gamma comma a, and then you go to gamma comma there is a z, a to the z. A to the z means that you restrict all the unbounded existential quantifiers in the formula by z. Okay. this rule here actually is the rule that captures delta zero collection in the infinitary system. Okay, and then one can do an ordinal analysis of this system, and since we have infinitary derivations here, and it turns out that you cannot allow arbitrary infinitary derivations, but you need to have a notion of a very controlled infinite derivation. And this leads to the notion of an operator-controlled infinitary derivations. I will just very briefly flesh this out. The main thing is that this operator somehow controls the ordinals from the ordinal representations used in the infinitary deduction. Yeah. And then once you do this, you can embed like in the PA case, you can embed the former system KP into the infinitary system. And then in the infinitary system, you prove catenation. And in addition to catenation, you prove a so-called collapsing theorem. And just bring it up very briefly. Now, where is it? The collapsing theorem here. And it's, so what happens here is basically there is a way of, the real obstacle for complete catenation is this sigma reflection rule, which is the rule version of delta zero collection. Yeah? And it usually, ordinary catenation is blocked because of this rule. But there is a way, namely if this gamma, if you deduce a set of sigma formulas, then actually you can, and you have a deduction of them for them, then actually you can get a cut-free proof of that. And this is engineered by the collapsing function, which exists in the pertaining ordinal representation system. And I haven't given you the details of that, and I won't. The thing is that this collapsing function is a modern version of what Bachmann did in the 1950s. Yeah. So his idea of using large objects to denote small objects is really crucial here. And okay, so you get a catenation also for Kripke-Planck. And I will spare you all the details. Okay. Okay, this is just the beginning of the ordinal analysis of strong theories. So this Kripke-Planck system is stronger than the first, how many are there? The first four systems of reverse mathematics, but it's weaker than pi-1-1 comprehension. Okay. And so the next goal then is to get an ordinal analysis of pi-1-1 comprehension. And this was already achieved by Takuti. And instead, I will give you the idea for a much, much stronger ordinal representation system, namely one based on delta 1-2 comprehension plus bar induction. Bar induction is basically, as I said, you have transfinite induction for arbitrary formulas over well-founded relations. And this is a theory which is actually very, very strong. It's much stronger than anything considered in ordinary reverse mathematics up to this day. And for this theory, I'd like to show you just briefly a Kripke-Planck version. And the Kripke-Planck version is actually easy to describe. You only need to add one axiom to Kripke-Planck, namely the axiom that says that every set is contained in an admissible set. An admissible set is a set, it's a transitive set such that the set is a model of cryptoplastic. So this basically is an axiom which you add to cryptoplastic saying the universe itself, or there are class many admissible sets in the universe, okay? And this is the theory KPI, which is actually the set-theoretic counterpart to the theory sigma 11a C plus bar induction, which is the same as delta 1-2 comprehension plus bar induction. Okay, and I will just briefly give you an idea of how you find an ordinal representation system which is strong enough to allow you to carry out an ordinal analysis for this. And here you basically follow the idea that was started by Bachmann. You imagine the existence of very strong objects, and here you imagine the existence of a strong object I, which is, well, which you can, for the time being, identify with the first weakly inaccessible cardinal. And then you also allow yourself a function which is called your capital omega sub alpha, which where the alpha in ordinals less than this I here. And the idea is that the successor terms of this form, omega sub psi plus 1, they stand basically for regular cardinals. You can identify them as regular cardinals below I, below the first weakly inaccessible cardinal. And then you develop a representation system based on this idea here. And the interesting thing is that in the case of the ordinal analysis of cryptoplastic, you just had one collapsing function. But here you will have to have collapsing functions for all of these large objects, for I, as well as for the large objects of the form capital omega sub psi plus 1. Yeah. So you have tons of collapsing functions, which are, and then in a similar way, similar vein as for cryptoplastic, you develop in infinitary formal systems. You have these terms, and this time you have terms L alpha for all alpha less than the big I here, and okay, and then you develop this infinitary system. And the crucial additional thing that happens is now you have the sigma reflection rule. You have this sigma reflection rule baked into the infinitary calculus for all large objects, for all the L pi here, where pi is either the big thing I, or it's of the form big omega sub psi plus 1. So you have all these reflection rules here in the infinitary system. But then what you need is to enable the cardinalization theorem and, more importantly, the coalescing theorem. You need tons of coalescing functions. For each of the big objects, you need a coalescing function. And it's really difficult to keep track of these. Again, you will need very uniform infinitary derivations with, but then you have this kind of very complicated situation that these coalescing functions interact, and that took a long time, very long time, took almost 20 years to develop this in a clear form. Okay, so to summarize now, a brief history of ordinal analysis. As I said, the birthplace is Ganson's ordinal analysis from, actually, there's a mistake, not so much 1936, it's 1938. And then Pfefferman and Schütte looked at so-called predicative systems in the 1960s. Takuti, a huge breakthrough when he did an ordinal analysis of pi11 comprehension. And then there was a lot of important work took place in the 1960s. Theories of iterated inductive definitions were very important in the 1970s. Buchholz did another kind of infinitary rules, the big omega infinitary rules. Girard looked at pi 1 2 logic, and the first person who really did the details about the proof theory of set theory was Gerhard Jäger, who dealt with cryptocratic at the end of the 1970s. And then, okay, the system I showed you, the KPI, was analyzed by Jäger and Polas, and then I did some stuff after that. First, I analyzed the theory KPM, where M stands for recursively Marlow. And in the pertaining ordinal representation system, we have a symbol M for M for the Marlow cardinal. And then what is new in the system also that in the systems before that, the collapsing functions had always values that were singular. And here in KPM, you actually need a collapsing function that also has values that themselves are associated with their own collapsing function. So, and a big technical improvement was the operator-controlled derivations of Buchholz in the 1990s. Controlling infinitary derivations is a very difficult task, and this was much helped by Buchholz's notion of operator-controlled derivations. And then this went up to higher representation systems than were based on ideas from larger cardinals. So, for instance, if you go up to pi 3 reflection, then you use an ordinal representation system which is based on the notion of a weakly compact cardinal. And then you can go up first order reflection, and you need something, the analogs of totally indescribable cardinals and more. Actually, when I worked on this in the middle of the 90s, I was at UCLA, and so I talked to Tony Martin about this, and I said I need cardinals that have this property, and then he suggested I should look at extendable cardinals, but I only needed something like supercompact cardinals, and actually less than that. Okay, and then, so here just another picture of ordinal representation systems and ordinal analysis. So we were here before, and when I use these kind of double lines, double vertical lines, it means it's a long, long way from the lower to the upper parts. So pi 1 comprehension, that's much, much stronger than anything that comes before. And then delta 1 2 comprehension, that's basically a variation of that. It's you do it not omega many times, you do epsilon 0 many times, but then going up to sigma 1 2a c plus bar, that is a huge step again. And then starting at the bottom with the system which was at the top on the previous slide, if you want to go up to something like pi 1 2 comprehension, it's a huge step up from there. And okay, and so I indicate this by lots of vertical lines, and some you get to pi 1 2 comprehension, but it's enormously more complicated than anything before. And so the situation, how is it today? It's basically that one can also do delta 1 3 comprehension, an analysis of delta 1 3 comprehension, but the real barrier appears to be pi 1 3 comprehension. And that's where it stands today, as far as I know. So now let me talk about something more concrete. So ordinal analysis was influenced also, you see, very much by ideas from set theory, from large cardinals actually. But in the end, you end up with an ordinal representation system, which is a primitive recursive object, which in some sense encapsulates ideas from large cardinals. And it's a fascinating area, I think. But you might ask, okay, what can one do with such ordinal analyses? And I would like to give you some examples. Of course, the first one is this extended Hilbert program, constructive consistency proofs. Well, so as I said before, the system based on delta 1-2 comprehension plus bar induction is really strong. Of course, it's wimpy compared to pi 1-2 comprehension, but it's really strong if you look at the systems that have been used in reverse mathematics. But when you compare it to, for instance, to constructive programs in constructive mathematics, there is, for instance, Per Martin-Löf's intuitionistic type theory. Yeah? But then it turns out that actually intuitionistic type theory can prove the consistency of delta 1-2 comprehension plus bar induction. Yeah? And there's a constructive consistency proof in Martin-Löf type theory. And what's interesting about it, well, how is this constructive consistency proof engineered? Well, it's not an interpretation of the classical system, the delta 1-2 comprehension plus bar induction. It actually works via the ordinal analysis. Actually, as it turns out, the ordinal representation system that you need for the ordinal analysis of delta 1-2 comprehension plus bar induction, that this ordinal representation system can be shown to be well-founded in Martin-Löf type theory. Okay, so it means that if you are a constructivist and think that Martin-Löf's type theory is the right way of doing constructive mathematics and encapsulates constructive reasoning in the right way, well, then you can at least say, okay, or whatever these classical mathematicians are doing, but if they prove, say, pi 0-2 statement in delta 1-2 comprehension plus bar induction, and then I have to accept that because it follows from the constructive consistency proof in Martin-Löf type theory that this pi 0-2 statement is also provable in Martin-Löf type theory. Okay. And then other rewards of ordinal analysis, okay, you get equiconsistency and conservativity results, and you also get independence results, and also combinatorial independence results. And okay, so what I just said, the consistency of basically sigma 1-2 AC, which is the same, I should stress it, as delta 1-2 comprehension, and then if you add bar induction, that you can show in Martin-Löf type theory. Okay. And now other applications, combinatorial independence results. And so on some of the very early slides, I said, well, actually, Ganson and Goodstein already obtained certain independence results. And in Goodstein's case, the Goodstein sequences that they terminate. There are other very interesting combinatorial theorems, and I would like to show you some of them. I think I have time for doing that. And they come from an area, well, which is not so, usually not so well covered in books and papers on reverse mathematics. And they come from an area which one could call the area of graph theory. And so what is a finite tree? A finite tree is what you think. It's just, it looks like a finite tree. So it's, formally it's a partially ordered set, B, which has the smallest element, where you have a relation, an order relation, less than smallest element B. And if you look at any element in B, then the things that are smaller than S, they are totally ordered. Okay, and then between trees, such finite trees, one looks at embeddings, and these are maps between trees that preserve some of the structure. So first of all, they should be injective, and then they should preserve the minimum relation of two nodes, A and B, in the tree. And okay, what does it mean to have the minimum of A and B? Well, if you look at a tree, so here we have a bunch of trees. So the minimum is, for instance, if you look at the left-hand side, if you look at the leftmost part of this tree here, and then you have these topmost nodes, and the minimum of these two nodes is the node immediately below, right? So it's always the minimum is the nodes immediately below. The node immediately below, there's only one. Okay, yeah. And then if you have two such trees, you're interested in maps that somehow preserve some of the structure, and the maps are the ones that are injective and preserve the minimum. Okay, so here's an example. So I can embed the first tree into the second tree, and what I could do is, well, I could send, you see, this node here. I don't know whether you can see my cursor. I can send this node, and so the top node of this tree in the first tree to this top node in the second tree, and I could then take the other top node, the rightmost top node here, and send it to that top node in the second tree. But then, because the mapping is supposed to preserve the minimum, well, the minimum of these two on the left-hand side is this node here, yeah. And if I look at the images of these two here, well, then the minimum of those is that one here. So I'm basically, I have no leeway here. I have to send this node to that node, yeah. Okay, so that's how these tree embeddings work. And, okay. And then there's a famous theorem, it's called Kruskals theorem. It says that if I have a bunch of infinitely many trees, then, and I enumerate them, then there cannot be total chaos. Namely, it means that for any such infinite sequence of trees, Bk, I can find an I, index I, index j, I less than j, such that Bi is embeddable into Bj in the sense I just described. And then, of course, there are infinitely many of such pairs by some Ramsey type arguments. Okay, and this a very important theorem of Kruskals. It was observed basically by Diana Schmidt and by Harvey Friedman, that this theorem cannot be provable in predicative mathematics, when I equate predicative mathematics with this particular type of predicativism, which was isolated by Pfefferman and by Schutter in the 1960s, based on autonomous progressions of theories, in which whose limit is the ordinal gamma zero, which is, by the way, is the ordinal of the system ATR0 of reverse mathematics. And it was observed by Diana Schmidt and Harvey Friedman that therefore Kruskals' theorem is not provable in ATR0 or in this type of predicative mathematics. And how did they observe this? Well, they basically observed that the well-foundedness of gamma zero, so this representation system, can be inferred from Kruskals' theorem. So basically, what you do is you assign trees to the ordinal representation system for gamma zero, which crucially involves the phi function. And then you see that an infinite descending sequence in the ordinal representation system would give rise to an infinite sequence of trees, so that it never happens that an earlier tree can be embedded into a later tree. And that's a contradiction to Kruskal's theorem. Okay, and a very nice application of this theorem was made by Ehrenfeucht. So there's the so-called polynomial exponential functions on the natural numbers. So what you allow is to start with the identity function x, and then constant functions, and you allow addition, multiplication, and exponentiation of such functions on natural numbers, and then you see, then you can actually order these functions by the relation of eventual domination, and it was a very important question, also unknown problem. The problem was unknown. It was unknown whether this ordering actually of eventual domination between polynomial exponential functions is well ordered. And it was proved by Andre Ehrenfeucht in a very short paper, and he used the Kruskal's theorem for that. Okay, now to a much more important theorem. It's the so-called Graph-Minor theorem. It was proved by Robertson and Seymour in a long series of papers, basically stretching from 1986 actually until 2004. This is on the right-hand side is Robertson, and the middle is Seymour. And this is a very important theorem in graph theory. Yeah. And, well, there's something about, it's similar to Kruskal's theorem. But here we look at the notion of a minor of a graph. Okay, the minor of a graph. So let's say we have two graphs, G and H. And H is said to be a minor of G if H is obtained from G by a succession of three operations. Namely, what you can do is you can first you can delete a single edge. And if you then find an isolated vertex, which is not connected to anything, you can remove it. And the third operation is most interesting here. It's if you have an edge between two nodes, you can contract it. Okay, and so here's just an example. So let H be this thing here, so just some kind of cross, and let G be, well, a more complicated graph. Then the claim is that this H here is a minor of G, yeah? And, well, how do you get from H to, how can you see that that H is a minor of G? Well, what you do to G, you first, you erase a bunch of edges, so the dotted edges, here you erase them, and that. And then you throw away the rightmost node here. And then the final step is that you make a contraction. You contract these two nodes here. I hope you can see my curve. So, and then you see, H is a minor of G. Okay. Now, with this notion of minor, there's an important concept in graph theory. It's forbidden minors. So if you have a class of graphs H, then you can look at those graphs G that do not have a minor in the class H. Yeah? So it means you look at those G's and those graphs that do not have a minor which lies in the class H. Yeah? Okay. And a graph property, can often be expressed by forbidden minors. Okay, so And okay, and so these forbidden minors are rather than the minimal ones. So if let P be a minor closed graph property, so it means if something is in P, the graph is in P, then also minor is going to be in P. And then there is a unique smallest set of forbidden minors, yeah? And this is KP, K sub P, not the cryptic project. And this is called the Kuratowski set for P, okay? All right. And it turns out that, well, we know some famous graph properties, for instance, being planar, so they can be characterized by those forbidden graphs, namely, they do not have k to the 5 or k33 as minus. Yeah. So here the Kuratowski set is just k5 and k33. But the graph minor theorem, what does it say? Well, the graph minor theorem says that if we have, like in Kruskow's theorem, if we have an infinite sequence of graphs, yeah, then we can find an index I and an index j bigger than I, such that gi is a minor of gj. And this graph minor theorem has an important corollary, namely that the Kuratowski set for minor closed graph property is always finite. Yeah? And it has also an abstract important corollary, namely that for every minor closed graph property P, membership in P can be decided by an algorithm in polynomial, actually even in cubic time. Basically, the algorithm, so for this algorithm, you need to know these finitely many graphs. Yeah, the finitely many forbidden ones. Okay. Yeah, also, I already mentioned what the graph minor theorem says. It says that if you have an infinite sequence of finite graphs, then there exists I and less than j, so the gi is isomorphic to a minor of gj. Okay, and some other famous conjectures by other people. Okay. All right, but now ordinal analysis comes into play, and namely what you can do is you can use ordinal analysis to show that the graph minor theorem is not provable in pi11 CA0. And the proof works while connecting ordinal representation systems with the graph minor theorem. Yeah. And so what you do here, and what is done in this paper by Friedman, Robertson, and Seymour, is that they show that the graph minor theorem implies that the ordinal representation one uses for the ordinal analysis of pi11 CA0 is well-founded. Yeah. What was not clear was that what is really an upper bound for the graph minor theorem. So the graph minor theorem is an outlier. It doesn't correspond to any of these systems in reverse mathematics. And there was a question, well, how far do you have to go to get a proof of the graph minor theorem in a system of second-order arithmetic? And this was an investigation that was mainly done by Martin Kronholz, a former PhD student of mine. And so what the real challenge actually was going through the proof of the graph minor theorem. And I said it was obtained, the proof was obtained over a long stretch of years, but it's kind of spread over 600 pages, over more than 20 papers, articles. And all of these articles are rather technically difficult. And so Martin, so I had to go through these proofs and to see where something happens that has an impact on the proof theoretic strength. Very often you have mathematical arguments and they can be very, very intricate, but you see there's no problem in doing them in any of these systems like ACA0. Then you have to really find the place where something proof theoretically strong happens or challenging happens. And so that was the challenge there. Okay, so I have 4 more minutes. Very briefly, I would like to say something about another application of ordinal analysis. So we have the ordinal analysis of cryptographic, and there is another version of cryptographic. So cryptographic doesn't have the power set axiom. But what happens if you add the power set axiom? Well, it's a theory that's much stronger than second order or such things, second order arithmetic. And let's look at even something a little bit, something stronger than even power set, just adding power set to cryptographic. Namely, so cryptographic is based crucially on the notion of a bounded formula. And now let's introduce a stronger form of boundedness. Let's call it subset boundedness. Yeah. So here we also allow bounded quantifiers of the form for all x subset of A. Yeah. And then one jazzes up, one increases the strength of the axioms from cryptographic by also allowing such bounded quantifiers, allowing subset bounded quantifiers as well. And then one has delta 0 subset bounded separation. So you allow also these kind of subset bounded quantifiers in the delta 0 separation, and the same in the collection. And then you get a system which is called power cryptographic set theory. Now this power cryptographic set theory is a very strong theory. It's much stronger than nth order arithmetic. It's stronger than Samelo set theory. Yeah? And there's a question of how much in the way of the von Neumann hierarchy can you prove to exist in power cryptographic set theory. And it turns out that first of all, that even power cryptographic set theory, even with AC, does not prove the existence of non-recursive von Neumann ordinals. And this was proved by Harvey Friedman in the 1970s. This proof uses Bauer's compactness and truncation. And then Adrian Mathias proved that KP plus power cryptographic set theory plus V equals L, the constructibility hypothesis, it gives you a much stronger system than the system power cryptographic set theory. And this was really a surprise, because usually if you add V equals L, it doesn't increase the strength. Okay, so now one can also use ordinal analysis to actually get a better result. And the better result is this, that cryptographic, power cryptographic, plus the axiom of choice, the full axiom of choice, if that system proves a statement A, which has, say, for all x there is a y, followed by a delta 0p matrix, then such a statement must already hold in the von Neumann hierarchy, where you go up to the ordinal, to this ordinal here, which is called the Bachmann-Howard ordinal. Yeah? And it turns out that one can do something similar to the ordinal analysis of cryptographic, but in a relativized form, where one uses some kind of formal analog of the von Neumann hierarchy. Okay, and just to say a little bit more, one can even prove this, the same statement here, this power cryptographic plus the global axiom of choice. And this is interesting because the usual way of getting the global external choice is V equals L, but by Adrian Mathias's result, we know that adding V equals L gives a much stronger theory. But it turns out that with ordinal analysis, you can show that if you add global choice, you do not get proof theoretically stronger theories. Okay, so I think that's enough. Oh yeah, that's enough stuff. And thanks for listening.